Okay, so hello everyone. The question which we are going to solve today is today's LeetCode POTD, which is lowest common ancestors of deepest leaves. The question number is 1123 and it is marked as a medium one. Okay, so now let's just read the description and try to solve this problem. Okay, given the root of a binary tree, return the lowest common ancestor of its deepest leaves. Okay. Recall that the node of a binary tree is a leaf if and only if it has no children. The depth of the root of the tree is 0 if depth of a node D, the depth of each children is D plus 1. Okay, I'll be explaining it. What does this mean? The lowest common ancestor of a set of S nodes is the node A with the largest depths such that every node in S is in subtree of root A. Okay, so what does this means? Let me just show you. Okay, so standing like can we divide it in levels like this tree? So can we say that this is the level 1 and this is the level 2, and can we say this is the level 3, and this is the like the level 4. Okay, so what like what is the deepest level? You can easily figure it out that it's level 4, right? Okay, so we have node 7 and 4. What is the least common ancestor of 7 and 4? It is 2, right? Okay, so the question is pretty much clear. Okay, like let me just add some more points to it, then I think that it will be much more clearer. Suppose there is a node 10 here, there's a node 11, and like suppose there is a node 12 and 30. So what are the like the deepest nodes? It is 7, 4, 10, 11, 12 and 13. Now when I ask which is the deepest node, like sorry, what is the lowest common ancestor of these nodes? It won't be 2 because it's not an ancestor of 10, 11, 12, 13. Okay, it can't be 0 because it's not an ancestor of 7, 4, 12 and 13. Similarly, 8 can't be the ancestor because it's not like an ancestor of 7, 4, 10 and 11. Okay, can 5 be a node ancestor? No, because it's not ancestor of 10, 11, 12, 13. Can 1? Probably not because it's not covering 7 and 4. Can 3 be our ancestor? Yes, because it covers 7, 4, 10, 11 and 12, 13. Right? Okay. So how are we gonna do it? Okay. I won't be going for recursion. It Don't worry. The solution will still be a big O of n, but like I will be telling you, I think that the way which I will be telling you, it's more intuitive, right? Okay. So before like I am using two concepts in it. Okay, so there are two concepts involved. Like the first one is, let me just write it, two concepts. two concepts which I will be using is finding parent of each node. Second is the BFS. Okay, so what I am trying to do here. Okay, let me just do the try run, then like I will tell you a coding trick also. Okay, we are gonna find both both the parent and the BFS in a single run. Okay, so let's just suppose there is a node here which is 10, and there is a node here which is 11. Okay, so what is the parent of, like, we are studying the parent, right? Okay, so where should I write the parent? Let me just write it somewhere. Maybe just a second. Let me just make some space here. Okay, so this is what. Okay, cool. So what are the parents? Let me just write it. The parent of three parents. Okay, so the parent of 3 is 3, like the ancestor. Like, okay, we can also, like, could have taken -1, but as a dummy node, but I am not taking it because I will tell you later why I'm not taking it. Okay, then the parent of 5 is 3, right? Okay, the parent of 6 is 5. Parent of 6 is 5. Okay, and the parent of 2 is 5, right? Then parent of 7 is 4. Oh no, sorry, parent of 7 is 2. Okay, it is 2. And the parent of 4 is 2, right? The parent of 4 is 2. Then what else nodes do we have? The parent of 1 is 3, and the parent of 0 is 1. Parent of 0 is 1, right? Okay, then the parent of 8 is also 1. The parent of 8 is 1, right? Then the parent of 10 is 0, and the parent of 11 is 0, right? Okay, parent of 11 is 0. Okay, okay, so let me just give you a brief idea like how we're going to calculate a parent. Okay, we're going to use map for it, right? So what the map will look like, it will look something like a map of a node pointing to a node, right? Let me just write it as parent. Okay, so this is how our map gonna look like, which will be storing parents, right? Okay, so like while doing a DFS, initially the its parent will be 3, then and the root will be 3. When we come to here, the root is equals to 5 and the parent becomes 3. Similarly, when we go here, the root will become 6 and the parent will become 5. In this way, we come here, the root becomes 2 and the parent becomes 5, right? So in this way, we are gonna cover like whole the parent, we are gonna map all the parents, right? Okay, so now just I'm asking like a something I will get like something. uh, I somehow figure out what are the deepest level nodes. Okay, so what are the deepest level nodes? It are 7, 4, 10, and 11. Okay, deepest nodes. Okay, somehow I got like using a BFS, I have got 7, 4, 10, 11. 7, 4, 10, and 11. And all these nodes are like they are nodes, not the values, right? This, see, this is a node. Okay, it's a node, it's not a val, right? It's not a value. Value are not, we are not gonna store. Okay, it's because like if you can see, we have to return a node. Okay, so we're going to storing the nodes. Okay, so a vector of nodes, we got all the deepest level nodes. Okay, so okay, it's like 0 1 2 3. We got 4 nodes. Okay, now we need to find a common ancestor, like the least common ancestor. Okay, can you tell me what is the like who is the parent of 7? It's 2, right? Okay, what, like who is the parent of 2? It's 2, right? Okay, who is the parent of 10? 0, right? Okay, who is the parent of 11? 0. Okay. Tell me one thing, that we have founded the parents, and are they all same? No, right? Okay, then what we're gonna do, just do the same step again. Who is the parent of 2? It's 5. Who is the parent of 2? It's 5. Who is the parent of 0? It's 1. And who is the parent of 0? It's 1. Okay, are all the parents same? No. Okay, do the same step again. Who is the parent of 5? It's 3. Who is the parent of 5? It's 3. Who is the parent of 1? It's 3. And who is the parent of 3? 1. It's 3. Okay, tell me one thing, that after this iteration we got something. What? All the parents are same, and it's the first time that all the nodes in the this vector have a same parent. So is it the least common ancestor which we were looking for? Yes, this is the least common ancestor which we were looking for. Okay, so this is how we're gonna solve it. We are gonna like just find the parent, finding the parent. Okay, so we're just gonna find the parent, and simultaneously we will be doing a DFS, and at the the least node we are gonna do this thing. Okay, so let me just show you the code, and then we'll be good to go, right? See, if you have any doubt like is this gonna work or not, it is gonna work, because these all are the deepest leaves. See, deepest leaves means that they are like an equal distance of level. Okay, so we at some point we are gonna get this answer. Okay, and we will just return it. Okay, so yeah, we're gonna mark the parent, and we're gonna just return it. Okay, now the coding part. Okay, I'll if you might be doing this way, I don't know, but this is how I do it. Okay, I'll be showing you the time complexity analysis. Okay, like it is taking big of an n. come here. Okay, now see it very carefully. Okay, I have taken an unordered map to store parents. Okay, okay. Then what I have done is I have taken a map which, like, the key is the integer and like the value is a node, like a vector of node. Why? Because with the help of this I'm gonna perform BFS, and with the help of this I'm gonna find the parent in a single run. Okay, I have called a function in which I have passed the root, the initial level which is 0, and the parent which is root itself, and I have passed the map, like the BFS one, and I've also passed the parent map. Okay, now come to the function. Taking the root, there's a level, there's a pair which is parent, and like we have the both maps. Okay, so if like root is null, we're just gonna return, right? Okay, now currently the level is 0, so map of level dot pushback root. Are you getting it? See, these all are the levels. Okay, this is level 0, so at the map of 0 we're going to push 3, right? Okay, this is level 1, so at the map of 1 we're going to push 5. Similarly, this is level 1, so at the map of 1 we're going to push 1, right? And for the 2, 3, oh no, this is also 2, this is also 2, and this is also 2. This is 3, this is 3, this is 3, and this is C. So the map of 2 will be containing all these elements, and the map of 3 will be containing all these elements. So at the max level we can just get what are the elements, right? See, I can do it, right? And what we're doing, we are just storing the root, like the parent of the root is pair, and we are calculating what the max level which we have reached. Okay, so that we can get in a constant time, like who is the deepest, like what are the deepest leaves, like the deepest nodes, deepest, what are the deepest nodes. We can get in constant time because we have a max level. It's a global definition, right? Okay, we are calling the left for the root left. We are increasing a level because, like, the deeper you go the level increases, and we are passing the parent as root and passing both the like the maps. And see, for the right also we increase the level because the level is increasing. Okay, it doesn't matter if you go left or right. Okay, and we have, and we passing the root, and similarly we are passing the map and the parent. Okay, so this is how we're going to do it, right? And we have just acquired the ARR, which have the, like, the max level I have told you. By this we're gonna get the deepest nodes, right? Okay, and I have, like, see, if the ARR dot size is equal to 1, which means that there's a single node, so we're just gonna return because it will be the parent, like it will be the ancestor of itself. Okay, the node should be greater. That is why I have taken something like, I haven't taken the dummy node. Okay, so, and we have taken an tree node type of answer, which is initially having a null PTR, and we have called a function help. Okay, so what this help gonna do? It will run until the condition is false. So let me just show you what the help function is going doing. Okay, see, I have like I replace the elements of the ARR with its parent and checking if all the parents are same. If not, we are just returning false, and at the end we are just storing like all the parents are same. So I'm just storing it into an answer and returning true. And if this condition is true, the answer is simply returned, and we will what? We will get our answer, right? See, I have turned like the see here what I was doing, that I was replacing it with its parents. So similarly, like the same thing I am doing here, replacing with their parents, right? And as you can see, we have solved this question. Okay, see the runtime, it I don't think like it's much of a deal, because you are solving the question and you have solved it intuitively, so that matters most. And talking about the time complexity, this is the official LeetCode's time complexity, which is big of n, right? Like if you click the analyze complexity, it will analyze it for you. Okay, so we have solved this question, right? So I think that you must be doing a dry run of this, and the things would be much more clearer if you do it by yourself. Okay, so yeah, thank you everyone. Have a nice day ahead, and yeah, that's all for this question. The code and the question link will be in the description box, there you can check it out. Okay, so yeah, thank you everyone.